Hello folks. Okay, well, we want to take a look at regional optimization this time. So we've gone through the local side of things, and next time around we'll get into subroutines, but for now we'll focus on the in-between. So again, now what we're looking at doing is taking more than just the information in a simple block. What we would like to do is kind of group blocks together, maybe take chunks of code around a block and try and analyze that together. So the most obvious things for situations like this would be to say, well, if we've got a little bit of code setting up for a loop, and then we've got a loop, then it's entirely possible we want to treat that as kind of one region, because I mean, logically, all of the information belongs together. It's all interrelated, and so we would like to somehow expand our analysis to include these extended blocks. So that's the goal next. So later on, we'll come back and in our data analysis section next week, we'll start getting into approaches to really try and identify what these regions might be. But for now, we'll think of it in terms of we've got some kind of a gateway, some sort of an entry block to our region, and then we're trying to encapsulate the set of blocks that fit in that region. And assuming we can create that, then we'll go ahead and look at some of the optimizations within the region. So that's where we'll leave that part for now, and we'll get into the data flow analysis next week. So one of the things that we'll take a look at in the regional optimization is just extending the value numbering system we looked at for local ones into our extended blocks. So that'll be the first thing we take a look at. And then we'll look at some customized variations that we can apply to loops under the right circumstance. Right? Loops are a key target for sort of regional optimization. So that seems like a logical place to try and tackle some of our ideas. So this extended numbering system. Again, the idea is we want a comparable idea to the value numbering that we used for the simple blocks. And we're just going to extend it to this bigger block. But we've got these problems in that if you've got sort of two blocks feeding into another block, then when you're trying to do your optimizations, when you're looking at that sort of convergence block, you can't really tell which optimizations might mess up one versus the other path. So we'll take a look at what this might involve. So we're going to represent our system as this sort of control flow graph where we've got a whole bunch of nodes that are our basic blocks, and then directed edges between them where one block can feed into another. So if you've got a branching situation, then one block might feed into two others. If it's a straight linear sequence, then it's just going to be a straight directed edge from block A to block B to block C to block D. So we'll take a look at our control flow graph and use that as the basis for trying to pick which of the different regions we're going to try and identify. And we'll start looking at sort of trees and paths within this control flow graph. So what we'll say is that because the places where these paths converge, the blocks that have multiple different incoming edges, because these are the sort of difficulty points in analyzing where information needs to be optimized. Do we optimize with the incoming path 1 or incoming path 2? We'll regard these as the sort of root blocks, the entry blocks for one of our regions. So those can't appear within one of our extended blocks other than right as the first one is the entry point. Now, within one of those, when we're looking at applying our local value numbering, we'll say, well, if I've got this nice linear path, A goes to B goes to C, and there's no branching to other blocks inside there, then I can look at that and say, well, if I consider that as just a straight linear path, I can take a lot of the value numbering optimizations that we used in our local value numbering system and apply them here. So what we'll try and do is identify these straight linear paths within the extended block that we've identified. And then we can pick up on some of the optimizations that can take place between the blocks that we couldn't pick up with local value numbering because it only looked inside the block. So that's the idea. That's where we want to go. So suppose we've got a control flow graph that looks something like this. We've got our 9 blocks here, B0 through B8, and we've got this sort of structure on where the branching goes between them. So At the end of B0, we've got, one of two destinations we can wind up with. So we've got sort of the equivalent of an if-then-else situation where we've got B1 or B2 that we're going to. And again, similar idea in B2, B3, or pardon me, B4 and B5 both feed into block 6. B3 feeds into B7 as well as B6. So these B6 here, since it's a convergent point, is going to have to be the beginning of one of our extended blocks. B3, or pardon me, B7, since it's also a convergent point, is going to have to be the beginning of a block. And then presumably our B0 is the beginning of an extended block, since that's the start of the region that we're examining. And the other one we've got that's a convergent point is B1 here. So we've got the two different paths that can feed into B1. So if we take a look at this and say, well, if we use B0, B1, B6, and B7 as our 4 sort of starting points for these extended blocks, then what do we wind up with? Right? B0, it can't include B1 because that's part of one of our other extended blocks. So B0 gets B2, B4, B5, and then has to stop before B6. So we get this kind of group of four blocks that we'll put in our first extended block. B1 can really only include B3, right? Because then we're back into one of our other entry points. B6 is essentially just going to be an extended block on itself, so there's not a lot we can do there. B7 can include B8. So we get these 4 extended blocks of, different combinations of the other blocks. So everything winds up in one of these extended regions, and then we'll take a look at what we can do within them. So again, within these things, we're just looking for the possible linear paths, right? For the B1, B3, it's pretty obvious. We've just got the one path, B1, B3. Same thing for B7, B8. We've just got the one path, B7, B8. B6 is a thing by itself. There's not much to do there. So the interesting one here is this combination B0, B2, B4, B5. We've got the 2 possible paths here. We can either go B0, B2, B5, or B0, B2, B4. So in terms of the different paths that we might wind up analyzing, these would be our combinations, right? The 2 possible ones that start at B0, the one possibility at B that starts at B1, the trivial one for B6 that essentially we've already covered with our local value numbering, and then the B7, B8. So what we'll do is basically say take each of these paths, treat it as a block for the purpose of local value numbering, and apply your optimizations within it. And so this is the point where we can start recognizing some optimizations between B0 and B2, or between B2 and B4, or across all 3 of them. And the same thing with path 2, and the same thing with path 3, and the same thing with path 5. So we're looking for opportunities to optimize across the blocks without messing up our other blocks. Now, one of the things that crops up in terms of trying to make the process more efficient is that when we're going through and doing the analysis of B0, B2, B5, and B0, B2, B4, obviously a bunch of the analysis data for B0, B2 is going to be the same when you process it in each path. So as far as trying to make this whole process more efficient, when you're actually implementing the compiler, you would get it to store state information about, okay, once I've analyzed the sort of top part of a tree, I'll remember that so that I can go through and complete the analysis with B5, do my optimizations there, and then back up and restore the information I'd remembered about B0, B2, and from that restored information proceed and do the B4 analysis with it. So you can start saving state information rather than recomputing it for every individual path in a tree where there's going to be a lot of overlap between the paths. So this is the general idea for trying to take our local value numbering and extend it across multiple blocks. Now, obviously, we're still not capturing all of the possible optimizations across all of the combinations of blocks, but we're making progress. We're getting there. We're recognizing more and more optimizations as we go. And as we start getting into wider and wider scopes of our optimizations, looking at subroutine optimizations and looking at whole program optimizations, we'll start capturing more of that information. All right, so if we've got the sort of separate paths idea, and for our or expanding our local value numbering to tackle that side of things, let's look at some of the optimizations that are specific to different structures. And what we'll focus on here are loops. Again, loops are one of the most commonly targeted sources of optimization, and there's a handful of techniques that are used over and over and over again to try and improve performance. And one of them is this idea of loop unrolling. So if you've got a loop that goes through 1,000 times and does, X within the body of the loop, what if we just had it go through 250 times and did X 4 times each pass through? Now, what's the point? The point is to try and reduce the amount of branching back and forth that we do, the number of times we test the loop condition and jump back and forth. So we're just eliminating part of that, part of the overhead associated with cycling through the loop over and over and over again. Right? The actual operations you're performing as the body of the loop are exactly the same. Right? They've got the same cost, you're just doing them with repeated chunks of code. So that does mean that your executable is getting larger, but your execution time isn't changing. And so as far as execution time goes, you're getting an improvement because you are getting sort of fewer of these jumps and branches, fewer of these tests and branches. So again, we can cut down the number of times we test the loop condition and jump to the start of the loop, pick up speed. The cost for that is we're adding extra lines of source code, right? So we're winding up with a larger executable because we're repeating the body multiple times. The other places where this gives us some advantages is if we've got this chunk of code that we're repeating this exact sort of chunk of code 4 times, for instance, in this particular case. If we think about the optimization ideas that we've looked at, there's a really high likelihood that if we're doing the sort of exact same computations over and over and over again, just the variable values are changing, that there are some good possibilities for optimization across those chunks. So it might be the case that the execution time and other resource costs for those 4 blocks is actually less than doing the 1 block 4 times, because we've got optimizations between the sequences of blocks or across the sequences of blocks. So, possible good targets for local optimization. The other thing that this might do is when we think of things in terms of our memory utilization, if we've got data values that are winding up on, in pages in memory that wind up in the cache someplace, there's a much better chance that if we're using this kind of approach, that whatever we're using in one of these blocks is already in memory from one of the previous blocks. At least a better chance than if we've just got this block by itself and we're sort of cycling through a loop where the loop tests and whatnot might be complicating life. So we might actually get better locality, we might get a better cache hit ratio. If we've got an instruction cache on our processor, right, where it's caching recently used instructions so that we can perform those again, then again we might get a better hit ratio for that as well. So there's all sorts of different optimizations and performance issues that might come out as an advantage if we take this process as well. Again, the cost being that we're increasing the size of our executable as we're doing this. So just another example of that. So that last one was a for loop. If we've got something like a while loop, we can do the same thing, right? We've got while and some test condition, do whatever the body is. Again, if we want to unroll that a little bit, we can go through and say, okay, well, again, we've got our test condition at the top, we've got our body, break if that condition fails, break if that condition fails. So now we're still having to test the condition. We've got a jump if we've hit the exit condition, but presumably, obviously the exit condition only gets hit once, whereas presumably we're going through the rest of it a bunch of times. So we're cutting down on the amount of branching that we're doing, the number of times we jump from one location to another. And again, hopefully we're providing opportunities for optimizations across the different bodies of this. So again, hopefully we're providing opportunities for improvement. On a completely different approach, one of the things that we can look at is looking at computation. If you've got something that's computed inside the loop that doesn't change across the paths, there's no point in computing it inside the loop over and over and over again. We want to compute it once and then just use it. So quite often the way to do that is to move it outside the loop. So in this case, let's say we've got something like a while loop where inside we say if, on some condition, then do one thing, otherwise do something else. Well, if that condition doesn't change, again, there's no point in recomputing it every time through. So we could compute it out here once and then simply use it. Or the other thing we could do is actually move the entire if statement outside the loop. And so, okay, if y, then we'll just repeat while x. So we're essentially inverting where we do the if and where we do the while. Now that does mean that the else, if y is not the case, then we also have to have the body of the, or have the while loop inside the body of the else, if you like. So again, we've increased the size of our code somewhat, especially if, this is a tiny example, but if the while loop itself is more complex, then we might wind up with a much larger executable doing this kind of thing, but hopefully improving execution speed. And again, it's entirely possible that we're opening the door for other optimizations by having this having the while loop sort of concentrated within the two halves of our if-else, rather than having an if-else breaking up the content of what we're trying to do. So, again, opportunities for optimization, opportunities for improved cache hits, right? We're just doing thing 1 over and over and over again in here. We're just doing thing 2 over and over and over again in here. Better likelihood for all sorts of different performance improvements in terms of cache hits and in terms of local optimizations. The other one I wanted to mention was loop splitting. So going back to the idea of our for loop, if we're going through and doing something 1,000 times, we could structure it as, for I is 0 to 1,000 or 1 to 1,000 or whatever, do the body. But there might be opportunities to say, well, what if we split that up into 4 chunks where we do, 250 runs of the body, and then the next 250, and the next 250, and the next 250. So exact same idea. We're just breaking this up somewhat. And again, for the most part, the goal of this is to provide opportunities for other optimizations to take place once we've broken it up. It might be the case that there are some natural breaks in this sequence where there are other things that you're doing in the code that will make, in the body that is, that will make more sense with one particular region than another. So there might be other opportunities there to sort of logically identify where to perform the loop splitting. But again, it's certainly a possibility. All right. Those are most of the things that I wanted to get through for the regional optimizations. A lot more possibilities will crop up when we get into the subroutine side of things, where we can take into account essentially the entire structure here instead of just pieces of it. All right, we will get there next time around.